So in today's session, we will be discussing about the deformation parameters of geomaterials. So one crucial deformation parameter, if you say take the clay soils, then it is the consolidation. So let us discuss the 1D compression parameters because mostly we deal with one-dimensional consolidation whenever we do any field problems. So here a typical void ratio and effective stress curve is shown here, and you know that the slope of the void ratio versus effective stress, or the void ratio versus log of effective stress, will give the compression index. So that is one deformation parameter. So here you can see in this typical graph, you can see the initially the soil when it is taken from the field, it is the virgin compression zone part is shown here, that is one. Then you slowly unload during the test, and then again you reload it, and again it follows the path of the virgin compression. So you know that for normally consolidated clays we take the compression index CC, but for over consolidated clay we take this part, the slope of this particular curve, which is the recompression index. So here it is elaborated that how you find the compression index. So as I explained earlier, it is the, you can see here, it is the graph of void ratio versus logarithm of applied vertical stress in the odometer test. So as shown below. So you can see here the void ratio is plotted again in the y-axis and the effective stress on the x-axis, and here it is given how the recompression index is obtained, how the compression index is obtained, and how the swelling or the rebound index is obtained. So you know that the virgin compression, when a virgin compression is actually the normally consolidated soil, that shows the normally consolidated range, whereas the pre-consolidation stress, the maximum pre-consolidation stress is actually in the region of the semi-elastic behavior. That means the soil behaves in a semi-elastic manner when the pre-consolidation stress is high. So that is actually the over-consolidated soils. And also in previous lectures I have shown you how the degree of pre-consolidation is expressed. That is, it is expressed using the over-consolidation ratio, where OCR, in the short form we call it as OCR, is equal to sigma p dash by sigma v naught dash, where sigma p dash is the pre-consolidation or yield stress, where sigma v naught dash is the current vertical stress. Now how will you determine the pre-consolidation pressure? So without knowing the pre-consolidation pressure, you cannot determine whether a soil is normally consolidated or it's over-consolidated. So the technique is adopted by Casagrande. It is a graphical method to find the pre-consolidation pressure, which we pre-consolidation stress. That is, it is obtained from the E-log sigma v curve obtained from the odometer test. So I'll just explain the procedure. This the steps involved in the method are given here. So I will just show the graph and I will explain how the pre-consolidation pressure is determined. So here this is the result of the odometer test. You have the void ratio on the y-axis and the effective consolidation stress on the x-axis. So this is the curve which indicates the initial, it's actually the recompression, because you take a specimen from the field, then you apply the stresses. So once you take the specimen from the field, what happens is that the specimen is already under some confinement by the surrounding soil, top and bottom soils. It is totally confined, and you are removing that particular soil for the test. That means that soil expands, some kind of swelling will be there as it is a clay soil. So again you are subjecting it to consolidation test. Means this particular portion is actually the recompression part, and again it follows the stress history. That means whatever stress it has been experienced in the past, that is being experienced after some amount of loading. So this straight line actually indicates the virgin compression. That is why it is called the virgin compression. Then you reload during the odometer test, and again you unload during the odometer test. This is the unloading path, and again you reload it. Finally it follows again the virgin compression, and you can find the CC and CR values. Now, how to locate the sigma p dash curve? So generally, if it is an ideal situation, that if you are taking the sample perfectly, that is, if you are taking the 100% undisturbed sample, then definitely this curve, where this curve is changing to a straight line, that point you can choose as the pre-consolidation pressure. But in most of the cases it is not possible. You cannot get a 100% ideal undisturbed sample, and in many cases we get the remolded sample, so you have to locate the pre-consolidation pressure. So how it is done? Using this graphical technique, which is the most accurate and simple technique. So the first method is first step is just draw a tangent to the steepest portion of this virgin compression zone. So here this is actually the virgin compression zone. So you draw a steep line, in fact a tangent to that vertical line. So it will be following that path of the vertical line only, because where it changes its maximum curvature to a steep line, you draw a tangent to that. So that will be the extended line of this virgin compression. Then what you do is you draw a tangent to the point of maximum curvature. So here this is the point of maximum curvature. So you draw a tangent to that point of maximum curvature. Now to that maximum curvature you draw a horizontal line, and such that that line bisects that curve. So again you have this horizontal line. Now you draw a bisector to this horizontal line as well as this tangent. That is number 4. And this line meets this particular line. That means the initial tangent which we have drawn. That point will be the pre-consolidation pressure. So just draw a line straight such that it finds a point on the x-axis. So that will give you the pre-consolidation pressure. So this is a very simple technique to find the pre-consolidation pressure. So you take the soil sample. As I told earlier, it is always not easy to get the perfect undisturbed sample. So definitely there will be sample disturbances when you take that specimen and you do the consolidation test. So what happens is that the laboratory E log sigma curve and the field E log sigma curve, there will be drastic changes. So whatever value, the compression index which you are determining from the lab to find the settlement, it is not the actual CC value which you are taking. Actually it will be different. So how to get such realistic settlement from the which is correlated to the field? So for that, Schmertmann developed another graphical procedure where a field virgin compression curve can be constructed from the laboratory consolidation test. Here in this figure you can see you are taking a clay sample from the field. So you take the sample from the field. This is the condition where you take the sample. That means once you take the sample, definitely, I told you the sample was subjected to some sort of confinement, and once you take it out, there is no confinement, so it will swell. So that rebound is shown here in AB, and then this dotted line here, which starts from A, this is actually the pre-consolidation pressure, and this is the dotted line where you can see this is the actual field virgin compression curve which you need. And this is the stress history, so it is continuing. So this will be the field virgin compression curve. Now in lab, when you take the sample for testing, this is what we are getting from the odometer test. That means due to sample disturbances, you get the laboratory consolidation curve like this. So you can't locate a proper consolidation pressure, pre-consolidation pressure. That is why you are adopting the Casagrande method. So this is a major issue, that the CC value obtained from this field compression curve as well as the CC value obtained from the lab curve is different. So that is why Schmertmann actually suggested a technique to get the field virgin compression curve from the consolidation test. Okay, so here he is explaining the procedure for finding the virgin compression curve. So I'll be just explaining the normally consolidated soil. No need of going to the over consolidated soil because it is slightly complicated. So we'll just go with the normally consolidated soil, how the field virgin compression curve is obtained. So this curve, this particular curve is the laboratory consolidation. So here you have the recompression, that means soil is getting compressed, then it follows the virgin compression path, then it is being unloaded. Now, after conducting the laboratory test, what you do is you calculate the initial void ratio, that is the void ratio before the test. So you have that value E naught here, and from that E naught draw a line, straight line, parallel to the x-axis, such that it meets the pre-consolidation pressure. So you have already determined the pre-consolidation pressure using the Casagrande method, and now this E naught, from this E naught you are drawing a line parallel to x-axis such that it meets the pre-consolidation pressure around here, that is point 1. Now what you do is you extend this normal consolidation curve or the virgin compression curve further, and you find a value 0.42 E naught. That 0.42 is actually obtained from the various research conducted by Schmertmann to finalize that value by for the corrections of the sample. That is, there will be sample disturbances, a lot of problems will be the transportation. So that is why he is using this technique to get the field compression curve. So this 0.42 is actually generated from that study. So 0.42 E naught he calculates, and you draw another straight line parallel to x-axis such that it meets the extended portion of the virgin compression curve, that is 0.2. Now what you do is you join this 0.1 and 0.2, that will give you this, so you get a curve which is denoted here as F. So that curve is the field virgin compression curve, and you can see the difference, that how it is changing. The laboratory virgin compression curve is slightly flatter compared to the field virgin compression curve. It is a steep slope. So this is how now you take the slope of this particular curve to find the compression index. So the procedure is given here in this slide. You can just go through the procedure how this field virgin compression curve is obtained, and it is very important that as a geotechnical engineer you must be very aware that how the laboratory curve is differing from the field curve. So now according to the Schmertmann procedure, you get the slope of the field virgin compression curve as the accurate CC, but then also you have to get an undisturbed sample to conduct the odometer test accurately, and getting an undisturbed sample is not always possible. So for remolded clay soils, you won't get a realistic CC value to estimate the settlement. So generally what we do is for ease, we just use some correlations to find the settlement, and that means you take the CC value using some correlations suggested by some of the researchers. So one such correlation, this you might have seen in your undergraduate classes as well, that is CC is equal to 0.009 liquid limit minus 10. Here LL is the liquid limit, and this is actually proposed by Terzaghi and Peck, and this is for a particular clay where the clay is of low to medium sensitivity. So all these correlations, whenever you see some correlations, that is for a particular study and for a particular clay. So we cannot use the correlations always, but to assess the settlement or to quickly assess the settlement, we can adopt such kinds of correlations. And this is another correlation where you use the natural water content. So it is directly, CC is 0.01 times natural water content. This was actually proposed for Chicago clays. And another correlation recommended by Indian standard, this IS 8009, is CC is equal to 0.3 E naught minus 0.27, where E naught is the initial void ratio. So based on the conditions and based on your requirement, you can adopt any correlations. There are further more correlations available in many books, or you can refer research papers to get the correlations of CC and liquid limit and CC and water content, whatever. But still it has some limitations, because correlations are always developed for a particular region and for a particular clay in that particular region and some fixed conditions. So the one-dimensional compression parameters, you can use it for all the settlements, especially for in the settlement of embankment, and also you can use it for the settlement of foundations. But what is actually happening in the odometer test? So you might have been gone through the video which I have shared for the odometer test, or you can even refer YouTube to see the test, how the odometer test is conducted. Already you have studied it in your undergraduate level also. But still I will explain that in the test, the specimen you are taking is actually 60 mm diameter and it is 20 mm height. So you can see that the diameter to height ratio is like 3 times, or even sometimes it is 4 times. And also it is actually in a ring, that you have a very strong ring and the specimen is inside that ring. That means you are providing confinement to that specimen, because you have to depict the field condition. That is why you are providing the confinement using that ring. So that specimen is inside a ring. And there is another thing, that due to that very rigid ring, there won't be any lateral deformation. But actually in the field, there will be lateral deformation to a, if you take a small specimen for field condition, despite of the confinement, there will be some lateral deformation. Also, you are providing a thick stones, that is you are providing the saturated stone on top and bottom of that particular clay layer specimen. So that means you are providing some compression from top and bottom. Due to that stone, there is some compression. Obviously you are applying the load, that is another thing. So due to these conditions, you will not get the actual field situation. That means the results you obtain from lab will not actually simulate the field condition. But there are situations where this field condition is very well depicted by the odometer test. That means if you take an embankment, a very large embankment, such that the thickness of that layer, of that clay layer, is very less compared to that area which is being loaded, then that is actually a 1D consolidation. Similarly, whenever a clay stratum is confined by strong stiff layers above and below, that means suppose just think that a clay layer is sandwiched between two layers of dense sand, then also it will depict the laboratory odometer condition. Now let us discuss about the deformation modulus of the soil. So why you need the deformation modulus of soil? So it is actually used to predict the displacements, either lateral or vertical, due to any applied load. That means the foundation can be foundation loading, it can be during excavation, tunneling, etc. So you need the deformation modulus or the elastic modulus of the soil. Now, if you want to predict the long-term deformations, long-term drained deformations, then you definitely go for the drained modulus of the soil. That means the modulus in terms of the effective stress. But if you want to predict short-term deformations or very small time, so definitely it will be the undrained deformation. So you go for the undrained modulus of the soil. That means there won't be any volume change. The soil will not be the volumes, because undrained means what? The water is not escaping from the pores. So that means there won't be any change in the volume of the soil. Now, how to get the design values of the deformation modulus of soils? So one such method is the laboratory test. Generally we do the traxel test. You can get the undrained as well as the drained modulus. So you have to take the very good undisturbed samples to conduct the traxel test. But that is generally possible for fine grained soils like clays and silt. But it is not possible. You cannot take the undisturbed sample for coarse grained soil like gravel and sand. So it is applicable for clayey soils. Definitely this usually the traxel test or the UCC test. In some cases, when you are taking very soft clays, you can do the UCC test to find the undrained strength. From that you can get the deformation modulus. Also you conduct the field test like the standard penetration test or the cone penetration test. So in the standard penetration test you get the N value, the blow count or the N value what you call, or in the CPT test you get the cone resistance or the tip resistance. So all these tests I hope you are studying in the subject called gift. So from that you will have an idea about N value and cone tip resistance, etc. So a lot of correlations are available for this N and QC, from which you can get the deformation modulus. Another correlation which you can take is, already I explained it, that is the UCC test. That means if you take the very soft saturated clays and there is no need of confinement for such kind of soil, so you apply the UCC test, and from the UCC test you just find the undrained, you get the unconfined compressive strength, and you divide it by 2, you get the undrained shear strength. You know how the UCC test is performed and what are the results, because already I have given a video also on this particular test. It's an elementary test. Anyway, once lab starts during the contract class, you will have a better idea of the tests, laboratory tests. And another method is by conducting the pressure meter test and the dilatometer test. It's also a good gives a good measure of the deformation modulus. Also, this test you will be definitely studying in the subject called GIFT. Now, these values generally give more realistic, reliable values. This test for coarse grain, whether it is a coarse grain soil or a fine grain soil or any residual deposits. Pressure meter test and altimeter test give the accurate results. So here in this slide you can see some of the commonly used correlations, very easy correlations you can use for field applications. So first one is the drained modulus for coarse grain soil, which is E is equal to K into N, where N is the N value obviously. K is the constant which is ranging from 1 to 1.5. Another correlation is for fine grain soil, where it is the same equation again, E is equal to Kn, and it is drain modulus, that is why it is mentioned as E dash. So here it is K value is changing between 0.6 to 7. Again K is multiplied by the N value. Now the undrained modulus for fine grain soil, definitely it will be for fine grain soils only. So it is represented as EU, which is equal to K into N. Here K is ranging from 1 to 1.2. And now for the drain modulus, obviously for long-term modulus, what I am talking about for fine grain soil. Generally for field application of fine grain soils, we need the quick results, we go with the undrained modulus. But in situations where you need to check the long-term deformation, you go for the drain modulus. So for drain modulus, it is E dash equal to K into Cu, where Cu is the undrained shear strength, and K it is ranging from 110 to 270. Similarly, the undrained modulus of fine grain soils, that is EU equal to K into Cu. Again, Cu is the undrained shear strength and K ranges from 500 to 1000. So these values, these equations you can use for field applications where you need to find the vertical or the lateral deformation of the soils. Now, when you talk about the intermediate geomaterials, that means obviously when you conduct the SPT test, once you go from the soil layer, then you are going to reach the rock. So in intermediate layer, definitely you can't call it as a rock, you can't classify it as soil. So you call it as intermediate geomaterial, but it is very strong compared to the soil. So you can't take the undisturbed samples of such material, and also laboratory test. The question of laboratory test is ruled out. And you cannot do the CPT because it is a very strong material, and you know the cone size in the CPT, and it is very difficult to penetrate that cone in such kind of a material. So definitely we use some rough correlations, like here you can see initially what I mentioned, the same correlation you can apply, that is E dash is equal to Kn, where K is ranging from 1 to 1.5, where N is the SPTN value. And then the other tests which you can use are the pressure meter test or the dilatometer test. So it is always suggested to use to conduct the pressure meter test or the dilatometer test to find the deformation modulus of the intermediate geomaterials. Next section is deformation modulus of rock masses. So for that you need to learn some parameters of the rock. So these sections I will be covering in the 4th module, where we will be dealing with the rocks. Okay, so that is the end of the lecture. Thank you.